Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone to this session again. So it's a great pleasure to introduce Sanjoy Dasgupta. Sanjoy is a professor at UCSD. He has been there for around 13 years. Before that, he was at AT&T Bell Labs as a researcher, and before that, he did his PhD from UC Berkeley. Sanjoy has been very active and has done some amazingly good work in active learning, clustering, and all sorts of machine learning problems. So, it's great to have him here, and I'm looking forward to all his lectures for the next 2 days. Over to Sanjoy.
Okay, thank you very much. So right now I'm going to, so I'll be talking about various different things, but right now I'll talk a little bit about active learning. And this is meant to be pretty understandable. So, if there's anything that is a little bit confusing or anything, please just ask straight away, okay? So active learning is rather different from the usual supervised learning model. And it's motivated by this observation that in a lot of cases, data is unlabeled, and it's easy to get lots of unlabeled data, whereas labels are expensive. Okay, so for example, if you're building a speech recognizer, it's easy to get speech. You just leave the microphone on and connect it. You get as much speech as you like. Okay, but in order to label that data, somebody has to sit down with the speech signal and look at it and decide what the phonemes are and exactly when each phoneme begins and ends. That's extremely costly. Okay, and so there's this sort of asymmetry between the unlabeled data and the labels that's really not part of the supervised learning model at all. And so the question is, what's a good way to take this into account? Okay, so the raw form of the data is just unlabeled. This is what you get, and you can get as much of this as you like, basically. This is free, okay? And what usually happens is that you pick a few of these. You say, well, it's going to be really expensive to label these. I can only, say, afford 8 labels. So you pick 8 of these points at random, and then you get their labels, and then you throw everything else away. And now you have these points, and maybe you fit a linear boundary to it, okay? Now, there are these other models, semi-supervised and active learning, that try to leverage the unlabeled data a little bit. Okay, so what happens in semi-supervised learning is that you pick those 8 points at random and you get their labels, but you keep the other unlabeled points around. And the hope is that somehow the unlabeled points bring out some kind of cluster structure, okay, that give you an idea of where the boundary ought to be, kind of between the clusters or something like that. Okay? Active learning takes things a little bit further. It says that you have all this unlabeled data, but instead of picking 8 points at random, try and pick them to be as informative as possible. Okay? You have only 8 things you can choose. Why don't you pick things that are, give you as much information as possible about the actual classifier? Okay? So just a quick example of how this, actually pans out. This was, so active learning is used a lot just because it's, it's necessary. And this was an example where they wanted to do pedestrian detection, and they put a camera on top of a car, and the car drove around the streets of Paris and collected many hours of video. Okay? And so there was just a huge amount of video. There's no way to label it all. And so what happened is that a few frames were picked out at random, and then a human put a box around the pedestrians. Okay? And that very small amount of labeled data was used to train some classifier. And then that classifier was applied to all the frames. Okay? And if there was something that the classifier was unsure about, the human was asked to label that. Okay, and so that was the way in which active learning was done. Build an initial classifier, okay? Have it make predictions, but also have this sort of notion of uncertainty or confidence. And then only ask for things that you are not confident about, and then retrain and iterate. Okay? And in fact, a lot of active learning methods look like this. Okay? So this is the typical way in which active learning proceeds. So you start with this large amount of unlabeled data. You pick a few points at random and you get their labels, just to kind of get the lay of the land, just so you know roughly where the boundary is going to be. And then you begin the actual active learning loop. Okay? Where what you do is you've got a few labels, you fit a boundary to the labeled data, and now you say, well, the points near the boundary are the ones that really I'm unsure about. These are the uncertain points. And so the next ones I'm going to ask for are these, let's say. And then you get those labels, and then you retrain, and then you keep iterating like this. Okay? And there are many different criteria that are, so sometimes you ask for the one closest to the boundary, or the one that is most uncertain, or the one that will most reduce the overall uncertainty. There are all these variations, but basically it's kind of the same thing. Okay? And so the question is, how good are these schemes? Okay? Because they certainly sound very sensible. And how can we analyze them? Because in supervised learning, we have all these, we have this really nice understanding of what the methods are doing. And so what really is going on here? How good are these active learning methods? Okay? And so how do we analyze this? And so we might as well do this in just the usual setting in which we always analyze supervised learning as well, which is the statistical learning theory framework. Okay? So in this framework, you say that there's some unknown underlying distribution on the data and labels. For example, the distribution of all street scenes in Paris, okay? Or the distribution of all documents from your document generating source, or whatever. There's some underlying distribution from which the training data comes and from which future test data will also come. You have no idea what this distribution is, but it's there, okay? And so there's this mysterious distribution P. Now you're going to build a classifier, and it's going to be from some particular class H, like linear classifiers, for example. Okay? And what you would like, therefore, is the classifier that does the best possible on that underlying distribution. Okay? The optimal classifier, the one that does the best job on the streets of Paris, for example. Okay? So the linear separator that does the best on that underlying distribution. Now, this is something that's well defined. The only problem is that we don't have access to it. We can't find it because we don't know what this distribution is. And all we ever get to see are a few points from that distribution. Okay? So we get to see n points from this distribution. And then we want to choose the classifier that does best on those n points. And then we hope that, as we see more and more data, this classifier that we've got will eventually converge to the best possible thing. So does that make sense? So this is the general statistical learning theory framework. So with this framework in mind, we can go back to active learning. Okay, so let's see what's happening over here. Okay, so now we have some unlabeled points. And what are these points from? They are from this underlying distribution P. Okay, so these unlabeled points have been generated from this underlying distribution. Okay, so let's see. We pick a few of them at random. In this case, we picked 6 of them at random, and we've got their labels. These 6 points that we've chosen at random are from the underlying distribution P. So we have 6 labeled points from the underlying distribution. And so what we do with those labeled points is meaningful. Okay? And so we get this initial boundary. Now we enter the active learning loop. And so we query some points near the boundary. And as time goes on, the points we're querying are really concentrated near the boundary. And so we get a data set that looks less and less like the underlying distribution. It's really a very weird data set that has no clear relationship with P. And it's not at all obvious that optimizing with respect to this strange data set will actually do well on the underlying distribution at all. Okay, so it seems like there's a big problem of sampling bias. Okay? And that really is the sort of central problem in active learning. Okay, you try to be really clever and to pick these maximally informative points, but what you end up with is a sample that's super biased. It doesn't look like the underlying distribution at all, and now you're trying to optimize with respect to that sample. Okay, so that's the basic problem. And so let me just give you a more concrete example, because I've just been explaining this problem in a somewhat abstract setting. So let's just look at a simple case where we have data that's just on the line. Okay, so this is 1D data. And let's say that that's basically in 4 clusters and there are 2 classes, the reds and the greens. So there's a big cluster here of reds. There's a big cluster here of greens, and then there are 2 clusters over here, okay? And so we start our active learning procedure. You're going to pick a few points at random. Since you're picking a few points, probably they'll be here and here, okay? And so your initial boundary, let's say if you're using a support vector machine, will be somewhere in the middle, somewhere around here, okay? And so now you'll begin your active learning loop. You're going to ask for points near the boundary, which means that you're going to be asking for points around here, okay? And as time goes on, you will converge to this thing, okay? So you're going to end up converging to this boundary. But that's not the right boundary at all. This boundary has got a 5% error rate, okay? Whereas the right boundary is this, with a 2.5% error rate, okay? So in active learning, we try to do well with very few labels, okay? But this is a case where even if you get infinitely many labels, this active learning procedure is converging to the wrong thing. Okay, so does that example make sense? And this is in 1D. What's basically happening is there's this cluster that is far from the initial boundary. And because it's far from the boundary, the algorithm's confident about it. Oh, I know what its label is. But it's never seen any labels in that cluster. So it's confident, but in this case, that confidence is misplaced. Okay? It was wrong, and it really should have asked for some labels in there. But that's not what these procedures do. Okay? And so if this is happening in one dimension, you can imagine that this problem is much worse in higher dimensions, where there are lots more places for these clusters to be hiding out. Okay? And so, so there have been nice studies, for example, where people doing text classification have noticed this sort of thing. They use active learning on this corpus of documents, and there are these entire clusters of documents that never get queried, and about which the system is completely confident, and it's wrong. Okay, so so what we look at is just ways to manage sampling bias, and to come up with. So what we really want are algorithms that are, first of all, at least consistent. So given enough labels, they do actually converge to the right thing. Okay, and then some idea of how many labels we end up using. Okay, and so there are 3 methods that we'll talk about, and it's sort of non-trivial to deal with this sampling bias. So before we get into that, I just wanted to address the question of, is it worth the trouble? Okay, so active learning clearly is not that easy. Okay, so sampling bias is a real problem. Is it worth the trouble? Okay, and so I'll just show you a canonical example where that sort of illustrates the power of active learning. Okay, so suppose that again we have data just on the line for simplicity, and that the concepts we're looking at are just thresholds. Okay, so the data lies on the line, and there's some threshold, and to one side of it it's plus, and to the other side it's minus. Okay, so really simple. Okay, and the data is actually separable, so they're really, it really does look like this. Okay, and so we just want to find the right threshold. So one thing we know is that, of course, we can never find exactly the right threshold with a finite amount of data. But if we want error less than epsilon, then we need about 1 over epsilon points. Okay, so if you want error, let's say, at most 1%, you need about 100 points. Okay, because if you take 100 points, then the gap between adjacent points will be roughly 1% of the distribution. Okay, so so that's what we know we need in the supervised learning case. Now in active learning, instead of 1 over epsilon labeled points, you can start with 1 over epsilon unlabeled points. And then you pick the point in the middle and you ask for its label. And if its label is a plus, well, then you look at the 25 percentile point and you ask for its label. And if its label is a minus, then you look for the 37.5 percentile point and so on. And in this way, you do binary search. And you locate the boundary with just log 1 over epsilon labels. Okay, and this literally, so in the supervised setting, you might have, say, needed 1,000,000 labels. Whereas over here, you would need log of 1,000,000, okay, which is 20, literally. There are no constants even, So, so there is this sort of exponential improvement in label complexity. Okay, and so this is the reason why people are hopeful about active learning. Okay, in order to achieve benefits of this kind. Now, this is a toy example. Okay, and so there are lots of problems. The first is that in this toy example, the assumption is that the data is really separable. You know, that they really are a bunch of minuses followed by a bunch of pluses. Okay, and in reality, nothing is ever separable. Okay. But in this case, it turns out that there is a sort of noisy binary search that you can do that would work just fine. Okay? So that's not a problem. The real problem is other hypothesis classes. This is just 1D, and we know how to do binary search in 1D. But in higher dimension, you know, we're looking for linear classifiers and things like that. How do you do a binary search through this sort of high-dimensional space? You know, what is the method for doing that? And it turns out that that's also something we can deal with. Okay? And so these are going to be the three methods that we'll look at. Method one is just to label everything. And that seems, I mean, it's not as naive as it seems. Okay, so let me explain what I mean by that. So this is method number one for active learning. Okay? And so here is one of the earliest active learning algorithms. It's just a really beautiful algorithm. It's from 1991. So that means that, you know, if I'm still talking about it in 2015, it means it must be really, really good, right? It has withstood the test of time, okay? And so this is an active learning scheme that is only for separable data, okay? But it's not just for things on the line. It really works for arbitrary hypothesis classes, okay? But it does assume it's separable. So if you're doing linear classifiers, it assumes that there really is some classifier that separates the pluses from the minuses, okay? So it's for separable data, and it works in a streaming setting. So you have this, you know, oodles of unlabeled data, millions of unlabeled points, and the way you get them is just one at a time, okay? And each time you get an unlabeled point, you just decide on the spot, do I want its label or not, okay? And so this is how it works. It starts by taking the entire hypothesis class, like decision trees or linear classifiers or whatever your class is, okay? And then it receives the next unlabeled point, and it has to decide, do I want its label or not, okay? And, well, it looks at the hypotheses. It looks at all these classifiers that are in its hypothesis class, and it says, do they all agree on the label? Do all of the possible classifiers think this should be a plus? If they do, I'm not going to ask for its label. But if 999 of them think it's a plus and one of them thinks it's a minus, then I'm not sure, so I'm going to ask for its label. Okay? And so if there's any disagreement at all about its label, then you ask for the label. Okay? And when you get a label, then you shrink the hypothesis class to include only those things that agree with that label. Okay? So, and then this goes on. So let me illustrate. Okay? So let's say we're running this procedure. We've already seen 7 points, and this is the 8th point. Okay? And let's say, so this is in 2D, and let's say we're using linear classifiers. Okay? So we get this new point, and now we have to decide, do we want its label or not? Okay? Well, based on the points we've seen so far, these are some of the candidate hypotheses. Okay? So our current version space, H sub t, consists of everything that's consistent with the labels we've seen so far, and these are some examples of them. Every one of them thinks this is red. Okay? There is no need to ask for its label. Okay? And so the only points that you would get labeled in this case are points that lie somewhere in here. Okay? And that's what we are going to call the region of uncertainty. Okay? And so if the unlabeled points lies in here, then you will ask for its label. Otherwise, you won't. Okay? So this is certainly an active learning algorithm. It kind of intuitively makes sense. But it's not the, you know, it's a very mellow algorithm. Okay? It's not really looking for maximally informative points. All it's saying is that, look, if we can be certain what this thing's label is, then we are not going to ask for the label. But if we have the slightest doubt, we're going to go ahead and get the label. Okay? So it's a completely non-aggressive method. Okay? But what we'll see is that it actually does extremely well, despite you know, not being super intelligent. Okay? But there are some issues. Okay? So the first thing is that maintaining the set of hypotheses is, in general, intractable. Okay? So let's say you're dealing with linear classifiers. You have linear classifiers. You've seen some labels, okay? And now you just want to keep the classifiers that are consistent with the labels you have so far. That's like some sort of weird body in high dimensional space. It's not the sort of thing you want to be dealing with, okay? The second is this only works if the data are separable, okay? Otherwise, this inference rule doesn't make sense. And finally, how many labels actually does this use? Okay, we would like a bound. Okay, we'd like to know, how does it compare with supervised learning, for example? And so we'll be able to deal with all of these things. And so let's do this one at a time, okay? So the first thing we'll do is to make it agnostic. And agnostic is just the word that's used for non-separable situations, which is the default situation, okay? Nothing is ever separable. Okay, so you have data. We are no longer going to assume that there's some perfect linear separator that separates the pluses from the minuses. It's the agnostic situation, okay? And we're going to make sure that everything gets a label, okay? But some points get labeled because we ask for the label, and the remaining points get labeled because we have inferred the label, okay? But everything is going to get a label. And that's how we avoid sampling bias, okay? So the problem with sampling, the reason sampling bias occurred is that we were just querying a few points and maintaining those labels. We're going to avoid it by giving everything a label, okay? Either we query it or we infer it. One way or the other, everything is going to get labeled, okay? Now, the invariant is that any labels that we figure out on our own, so there's some point which we think really should be a plus, and we fill in that label by ourselves. That label will agree with the optimal hypothesis. We'll make sure of that, okay? Okay. It might not be the label that we would have got if we queried the point, because the data is not separable, but it will agree with the optimal hypothesis. And we will never need to maintain diversion space, okay? And to make this happen, we are going to use a black box that takes this label data and then finds a linear separator that agrees with all the points we've inferred and minimizes error on the queried points. And so let me just show you what this algorithm would look like. Okay? So this is the agnostic version. Okay? So initially, so all our points are going to get labeled. Some will be inferred and some will be queried. Initially, both sets are empty. Okay? And now you keep getting these points, and for each one you have to decide whether or not you want its label. Okay, so here's what you do. You get a new unlabeled point, and what you do is you try all possible labels. Okay, you say, well, let's first try giving it a label of 1. Okay, so you give it a label of +1, and then you feed it into the black box along with all the other labeled points you have, and you get back some classifier. Now you say, let's try it with a label of -1. Okay? And again, you feed it into your black box learner, along with all the other label points that you have, and you get back another classifier. And now you look at the error of those classifiers on the label points that you have so far. And if one of them is much better than the other, if H plus is way better than H minus, then we know the label must be +1. And if H minus is way better than H plus, then we know the label must be minus. Otherwise, we ask for the label. Okay? And so this is the way it works. Okay? So you keep around all the, you keep getting these points. For some of them, you ask for the labels. For the rest, you fill in the label. Okay? And each time you get a new point, you just try both labels. You try it with a +1, give it to your black box along with all the other data, and get back a hypothesis. You try it with a -1, get back another hypothesis. And now you look at the relative performance of these hypotheses on the data that you have. And if one is much better than the other, then you don't need to query the label. Okay? Mm-hmm.
So when you go into every time you create a model, new model, using different types, so when you're calculating the errors, there would be a chance of overfitting with one of the models when you're creating the data and creating a new model. So is it like creating an error you do cross-validating, which I think is a very costly operation over the data to get the right error according to this?
Right. So what happens is that so you get these two classifiers, and if one of them is much better than the other, then you don't need to ask for the label. Okay, like if H plus is way better than H minus, then you say, okay, the label must be plus. But the question is like, what is that gap? How large does that gap have to be? And that gap just comes directly from generalization bounds for supervised learning. Okay, so it's like 1 over square root t, or one of those standard generalization bounds for supervised learning. Now, and built into that will be any so these bounds hold with high probability, but as you pointed out, you're using these bounds every single iteration, right? And so the failure probabilities are adding up, and so you have to work that into the bound, okay, to make sure that they add up to something small, like 1% or whatever you want them to be. Right, so for calculating the error, yeah, so for some points you have the actual labels, and for other points you just have the label that you filled in, okay? And it turns out that that's good enough. Because you're looking at the differences between these errors. So even if you filled in the wrong thing, you're shifting both by the same amount somehow, okay? That's sort of, it does seem like, although you're labeling everything, you are introducing sampling bias by filling in some of the labels yourselves, right? I mean, one of the labels you fill in might not, for instance, be the label that you would have got if you'd queried. Okay, so that does seem like it's introducing bias into the labels. But it turns out that whatever bias there is, and there is bias, cancels out because you are taking differences between. Okay?
I don't know if you're doing this, trying to run this example, the line thing there,
I wasn't going to show that, but yeah, we it's been tried out.
order of points?
No, random. All right, so this is always for random ordering. Okay, and anyway, so basically, at the end of this procedure, I mean, throughout the procedure, the guarantee ends up being that the labels you infer might not have been what you would have got if you actually asked for the label, but they are consistent with the optimal hypothesis. Okay? And so in this sense, the inferred labels are better than the queried labels. There is some optimal hypothesis. The inferred labels always agree with that hypothesis. The ones you query sometimes do, sometimes don't. Okay.
High probability is over the randomness of the order, or any of that high probability?
Right. The high probability is over the randomness. So one way to think about it is that each point you see is generated at random from the underlying distribution. So it's with high probability over that. This algorithm does not have other randomness in it.
It seems like the points that we take first, they'll greatly depend upon the points that we query in the first place. So the initial set of points, let's say they all belong to one class. So subsequently, whatever we infer from it will also be sort of skewed by that initial set of samples that we query. So how do we sort of deal with that?
Right, and that's why basically, we're assuming that the points are generated at random. So it's not like you're seeing all the pluses and then the minuses. So if you do have a data set, then what you would do is to start by randomly permuting it. Okay. Yeah. Any other questions? Yeah.
Each new data point, so training the entire model without aspect again, is scalable performance like training will take some time.
Yeah, so I'll get to that. So right now, this is a time-consuming thing, because for each data point each time you get a new point, you are trying it with a plus label and a minus label. So you're learning two classifiers for each new point that you see, right? So it's polynomial, but it takes a long time, and so we'll talk about that later. Okay. Okay, so this is well and good, and it's consistent, which is good, but what we'd actually wanted from active learning was to have a very low label complexity, to show that you can get error epsilon by asking for very few labels. Okay, so how many labels do you need in order to get error epsilon? We know the answer for supervised learning, so that's been studied very carefully. We know very good answers. What is it for active learning? Okay, so for supervised learning, sample complexity depends on the VC dimension of the concept class. Okay, so if you want to get error epsilon and your concept class, if your linear separators in D dimensions, the VC dimension is D or D plus 1. Okay, and that's what it depends on. Okay, if you want error epsilon, you need D over epsilon labeled points, roughly. Okay, it turns out that for active learning, there's another parameter that matters, another parameter of the concept class called the disagreement coefficient. Okay, and this comes up in active learning. Okay, so let's look at that original algorithm from 1991, Cal. And that was only for the separable case, the Kohn-Atlas-Landner algorithm. Only for data that's actually linearly separable or whatever your concept class is. Okay, so for supervised, we know that we need D over epsilon. For that algorithm, this is how many you need. D times that other constant times log 1 over epsilon. So it really is that same exponential improvement, okay? The dependence on epsilon is just a log. So if epsilon is 1 over a million, this really does become 20 instead of a million, okay? And so, and that's a pretty remarkable thing, okay? Because that algorithm doesn't seem like it's trying to be too clever, okay? And it turns out that the similar things hold in the non-separable case, and there are lower bounds and so on. Okay? So, so these are algorithms that, so as I said, in active learning, the main problem is sampling bias. These are algorithms that deal with the sampling bias, and they have these very good bounds. Okay? So everything seems good. But there are problems in practice. Okay? And so here are two rather big problems. Okay? The first is that these generalization bounds for supervised learning, normally the way in which we use them is just to understand learning procedures mathematically. Okay, so we want to know, we have a decision tree versus neural net. Which of them needs more data? You know, we just want to, it's just for that sort of an intellectual understanding of these algorithms. In these active learning procedures, the generalization bounds are being used inside the algorithm. Okay, so now generalization bounds are known to be pretty loose. Okay, and using loose bounds inside the algorithm leads to methods that are overly conservative. They end up asking for way more labels than are actually needed. Okay, so that's the first problem. And the second problem is that, let's say you're dealing with linear separators. On each step, it asks you to find a linear separator that's consistent with the data so far or makes as few errors as possible on the data so far. That's an NP-hard problem. Okay? So finding a linear separator that minimizes errors on the data you've seen is NP-complete. That's not a problem we know how to solve. Okay? And in machine learning, the way we usually deal with that is to abandon that as our goal. We pretend that's not what we really want. Okay? We say, oh, well, we didn't really want to minimize the number of mistakes we made. We instead wanted to minimize this convex surrogate, okay, like the squared loss or the logistic loss or something like that. Okay? And so that'll lead into the second method for active learning, which is importance weighting. Okay? So, so let's look at more general loss functions. Okay? And as I said, this is one of the reasons we do this is because the most intuitive loss function is the 0-1 loss, where you get a penalty of 1 for everything you get wrong and a penalty of 0 if you get it right. That loss function is unfortunately intractable to deal with in general. And so people end up using these convex loss functions like the squared loss and so on, okay, where it's kind of a gradual thing. You get 0 if you get it right, and then, loss. Okay, so so then the setup changes. So now you have an input space and you have a label space, which might be +1 or -1. But now your hypotheses, like your linear classifiers, instead of outputting +1 or -1, might say output a real number, where you would interpret a positive number as being a plus label, and a negative number as being a negative label. And then there's a loss function. For example, for logistic regression, this is the loss function over here. Okay, and this is a convex loss function. Okay, so previously we were talking about 0, 1 loss, but now just look at a general loss function, okay, where the thing we want to minimize is that we have this underlying distribution, we have the true label, we have the data point, we have our classifier, and we want to minimize the loss of what our classifier says with respect to the true label. Okay? And this could be 0, 1 loss, but it can be also one of these other convex losses that make optimization easy. Okay, yeah?
A couple of questions relating to your previous results. There is presumably a dependence on the distribution in the order sample complex generating this. In some sense, what are the worst case distributions?
Oh, what are the worst case?
So I could take like an infinite number of unlabeled samples, learn the distribution first, and then try and do something which picks only the important, the most likely points in the distribution to learn.
Right, yeah, no, there are definitely, so even for linear classifiers, for example, there are some very bad distributions. And, right, and so those, and we have a pretty good idea of what those are. And for those distributions, so this parameter depends on the distribution, okay? But we have nice bounds on it for any smooth distribution, say, right? Okay. Basically, the worst distributions you can think of are discrete distributions, where, like, let's say you just have a certain number of points, and each point could, just have a different label, say. Or, there's just, it's just constructed in such a way that you're somehow forced to query all of them. Okay. Okay, so any questions about this? So this is exactly what we were doing before. We get a bunch of data, and previously we just wanted to minimize the fraction of time our classifier disagrees with the true label. And now we're saying, let's just do something more general, okay? We just want to minimize the loss of our classifier's output with respect to the true label. Okay, this is the true label, this is what our classifier says. We want to minimize the loss between these two. Okay, so we're now allowing loss functions that are not just 0, 1. Okay? So this is how active learning can proceed in this case, okay? So we are no longer going to label everything. We're just going to ask for a few labels, okay? We're not going to fill in the rest. We're just going to ask for a few labels, that's it. The difference is, when we ask for labels, we're going to put weights on points, okay? So we're going to use weights, and so we'll use importance sampling, okay? So initially, our label data, we haven't asked for any labels, and now we start this loop where we get one unlabeled point at a time, and we decide whether or not to label it, okay? So you get a new unlabeled point. Now, instead of making a hard decision, like, oh, I definitely want its label, or I don't want its label, you instead choose a probability. So you get this new unlabeled point, and you say, let me give this a probability of 0.8, which means that you're pretty likely to label it. So then you flip a coin, and with probability 0.8, you ask for its label, and with probability 0.2, you don't ask for its label, okay? Now, if you do end up getting its label, then you add the point and the label, and you give the point a weight 1 over that probability. Okay? So it becomes randomized. Okay? And this is an importance weight. So with each new point, you don't decide, I'm definitely going to label it or not. You just pick a probability, 0.1 or something like that. Okay? And now, you find the classifier that minimizes the loss on the points you actually labeled, but where each point has got that weight, 1 over p sub t. And one thing you can show is that this is an unbiased estimate of the actual loss. Okay? It's the unbiased estimate of the loss using all points. Okay? And so let's just see how exactly this works. Okay? So, so for each point that arrives, you've chosen this probability, and so there's some probability that you will actually query that point, okay? And so let's call that event Q sub t. Q sub t is the event that you're actually going to ask for the label of the tth point. Okay? Now the expected value of Q sub t is just P sub t. That's the probability you're going to ask for that label. Okay? And the loss function that your loss function at time t is this. Okay? Because if you don't ask for a point's label, then this is a 0, and so that point does not appear in the loss function. If you ask for its label, then this is a 1, and it appears with weight 1 over P sub t. So this is the loss function you're working with. Okay, this is the loss function you're working with, and its expected value, well, the expected value of this is P sub t, so that cancels out, and so the expected value is the actual loss. Okay, so the probabilities have been rigged so as to remove the sampling bias. Does that make sense? So this is a sort of a pretty easy way to ask for just a few of the labels. Okay, and then you can show some sort of generalization bounds for this. And the nice thing about this scheme is that you can use any way of setting the probabilities. For example, one thing you could do is to fit a classifier to the data you've got so far, and if a point is near the boundary, then you assign it a low probability. If it's far away, you assign it a high probability. If it's far away from the boundary, you assign it a low probability. Okay? It doesn't matter how you choose the probabilities, this will always be consistent. Okay? So this weighting trick removes the sampling bias. Okay? Now there's a specific way of choosing the probabilities, I should say, that actually gives you the kinds of bounds we were talking before. And I won't really, let me not get into the details right now, but there is a way to choose those probabilities that gives you those kind of nice results. The log 1 over epsilon type of results that we were talking about before. And it involves solving 2 convex optimization problems for each new unlabeled point that you see. Okay? But that's still better than what was happening before. Okay, where you had to solve 2 0-1 minimization problems for each unlabeled point. So I'll just give you a quick example of this, just to see what some of the curves look like. Okay, so this is an example with 2 Gaussian classes, so you're learning a linear separator in 10 dimensions. Okay, and there are 2 Gaussian classes in which the overlap is 5%. So it's not separable. Okay, but it's really well behaved. Gaussians are, really nice. Okay, and so this is not separable, but as far as non-separable goes, it's pretty benign. Okay, and so you run this procedure, and this is the number of unlabeled points seen, and it seems to do fairly well. By the time you get to 500 unlabeled points, it's asked for maybe 65 labels. It sounds good. So it's something that, can actually be implemented, okay? And I'll say a little bit more about that in a second. But I wanted to show you another curve, okay? So the algorithm looks very nice when you look at this curve, okay? Because here, look, that we got 500, we had a data set of 500 points. We ended up labeling only 65 of them. That's pretty nice. But this curve is actually a little bit more interesting, okay? Because this is comparing what happens with supervised learning. Okay, so what this shows is that initially, active learning has essentially no improvement over supervised. Okay, so and the reason for that is initially you just have no idea what's going on. It's only when you have a fairly good sense of the boundary that this so-called exponential improvement or anything like that kicks in. And so it only kicks in towards the end. And when you draw the picture like this, the difference doesn't look anywhere, as impressive as it looks in the other picture. Okay, so you can keep one picture or the other in mind. I actually think this picture is the more interesting. This kind of shows what's happening. You need to get the error down to a certain level before the active learning really kicks in. Okay, and okay. Is there any questions about that? Okay, so so this is a lot more practical than the previous scheme, but it still is based on loose generalization bounds, And okay, but it turns out that you can actually develop a very practical version of this by just replacing the steps by. So the basic importance weighting idea is solid and easy. Okay, there's not, that's really easy to use. Okay, but the problem is that in order to set these probabilities in a way that would give us these querying probabilities in a way that would give us these very good label complexities, we were doing all sorts of complicated stuff. Okay, and so but there are ways to just sort of approximate that very crudely. And for example, the current version of John Langford's optimization package has this built in, where instead of solving a convex optimization procedure on each step, you just take whatever you had in the previous step and you do one stochastic gradient descent step based on the new point. Okay, something like that. Okay, so very crude approximation, and that seems to work okay. Okay, although there's very little theory about it. Okay. Okay, so finally I'll get to the last active learning scheme, and this is a very simple and practical method. Okay. And so here's the motivation. Okay, so you have a lot of unlabeled data, and suppose it looks like this. Okay, so you look at it, and there really seem to be 5 clusters over here. Okay, well then maybe it's easy. Maybe you can just ask for one label in each cluster, and you're done. Okay, so you ask for a label here. It turns out to be red. You say, okay, this is the red cluster. Okay, so this is kind of a dream scenario, but it's like overly optimistic. So what are the problems? Okay, so there are 3 issues. The first is that the cluster structure is usually not so clearly defined. Here the clusters are just really far away from each other. Okay. The second, and this might be another way of restating the first, is that typically there's structure at many different levels of granularity. Okay, there's a reasonable way to divide the data into 3 clusters, but then you could also divide them into 10 clusters. There's like many levels of structure, and it's not clear what level of granularity you should be operating at. And finally, even if you do have a cluster that seems like, pretty coherent and far away from everything else, there's no guarantee that that's going to be pure in its label. Okay? So how can we sort of accommodate all of these and do something reasonable? Okay? And so here's the basic primitive, which does not work on its own, but we're going to put something around it that makes it okay. Okay? So we find some clustering of the data. Okay? Who knows how? And now what we'll do is that within each cluster, we'll randomly pick a few points and get their labels. So in this case, we've decided that we're going to pick 5 points inside each cluster, and for some reason 4 inside that one. And we're just going to, we're going to randomly pick 5 points, get their labels, and then we're just going to assign the majority label to the rest of the cluster. And when we do that, we get a fully labeled data set, and then we can use that to train whatever classifier we like. Okay, so really simple. So now let's see how this would actually work out, okay? How we really need to do this. So we have unlabeled data. Now we find a clustering, okay? Let's say we find those 2 clusters over there. Now we're going to ask for labels. And now the most important thing is the following rule. You are not allowed to ask for the label of a specific point. You're only allowed to ask for labels within a cluster. So if I want 6 labels, I have to pick 6 points at random inside this cluster. I'm not allowed to say, give me the label of that one. Okay, so I just choose a number like 6, and let's say I get 6 points inside that cluster. 6 points are randomly chosen for me, and I get their labels. And in this cluster, let's say I asked for 8 points. 8 points were randomly chosen for me, and I got their labels. Okay? Now, based on this, I'm feeling pretty good about this cluster. I'm ready to make it the all red cluster. But this one is looking a little bit more iffy. Okay? So what do? Well, then I just refine the clustering. Okay? And so now I partition this further. Okay? So let's say I divide it into these 2 regions. And now the key thing is that, see, the points these points over here were randomly chosen in this cluster, which means that the ones in here are actually random within this cluster as well. So there's no sampling bias, okay? Because I randomly chose within the original cluster, when I split, it still remains random, okay? And so the sampling bias thing is taken care of. And now at this point, I might be happy with this, and I might need to split this further, okay? Right. So, right. It depends on whether that label was used both for the splitting and for the accounting. Yeah. So each label has to serve one function or the other. Okay. So yeah. And so one way to see this is that you just start with a hierarchical clustering of the data. Okay. So you start with a hierarchical clustering. Either based on no labels or based on a few labels. Okay, so you start with a hierarchical clustering, and then you go to the top of the hierarchy, which is just one cluster containing all the points. You pick a few of those points at random. If everything looks pure, you're done. There's only one label, everything is that label, okay, but that's not going to happen. So then you go down to the next level of the hierarchy, and now again you are allowed to sample at random in here, sample at random in here, and if something looks pure, then you can leave it. Otherwise, you go down to the next level of the hierarchy and so on. Okay, so it's a very simple method. Yeah. Right. So what's okay? So there are two different thresholds. The first is that if at any given point I'm forced to assign a label to this cluster, I'm always going to use the majority. Okay, so that's easy, right? The other thing is, what threshold am I happy with? Okay, like over here, should I be happy or not? Okay, and that is, I don't know, how one chooses that. Sorry? There might be label imbalance. So the thing is that is one aspect of the problem. So this scheme has been studied quite a lot, okay, because it's so simple and nice and so on. But this is one aspect of the problem that has not been figured out, okay? And so basically one way to think about this is that at this point, we might decide we're happy with this, okay? And work on some other region of the space where everything is much more mixed up, okay, where you have an equal number of pluses and minuses. So we work on that other region, we divide it up. Once that region becomes more pure, we might want to come back to this one and then say, okay, we were happy with this, but now our overall level of accuracy is so high that we have to come back and work on this. Okay, and so the exact protocol of doing that has now been worked out properly. Okay, that's a great question. Yeah. Here.
You broke into two clusters. That's how you do it.
Oh, you just use whatever your favorite clustering method is. Mine is average linkage clustering. Okay, there's no. So you use you just use whatever clustering method you like. Okay, some of. Well, these hierarchical schemes actually, they give you an entire tree, and so so you don't have to make any decisions. The main decision you have to make is what the distance function is that you're going to use on the instances themselves, and for that you use whatever domain knowledge is possible. One thing that would make sense is to use a few labels in constructing the hierarchy, but that's something that is not known how to do. People don't have a good way of doing that. Suppose suppose you have 1 million points and you have labels for a few of them, and now you want to construct a hierarchy that somehow takes those labels into account as well as respecting the geometry of the points. How do you do that? Unclear. Yeah. Oh yeah, so that could be determined by what level of confidence you want, just from standard statistical confidence intervals. If you want a 95% confidence, then you need so many points and so on. So the statisticians would do that just based on a normal approximation.
If we make number of clusters many more, and then we recombine them, like in this approach we are going further defining more clusters. If we recombine the more clusters into less number of clusters, how that approach is? Like if we divide the given data points into 10 number of clusters, and then we go for joining 10 number of clusters into like this tree.
So a scheme like that would, so over here, I mean, although it's a very nice, simple scheme, the key feature of the scheme is that somehow sampling bias has been taken care of. And if you were to recombine clusters, then that would again become an issue that would have to be dealt with somehow. Okay?
So let's just say I have lots of documents which are unlabeled, and I would like to put them in some categories or some clusters. So what would be my initial way of clustering them? I mean, if I would like to do this in that.
Yeah, so what you would do, well, for documents, the default thing you would do is you would start by fitting a topic model to the corpus, okay, with lots of topics, right? So like 200 topics or something like that. So you fit this topic model. So now every document has this nice 200 dimensional representation, and now you build a hierarchy on that. So that, that would kind of be the default. But there's probably better things one can do. Okay. So, so the main things are, what are the way for building the initial hierarchical clustering? You can pick whatever you like. Rule for deciding which cluster to query. You can pick whatever you like. And when do you move from a cluster down to its children? Again, you can pick whatever you like. And different people have looked at different rules, and you can prove bounds and so on and so forth. Okay? So the bottom line is, I think the fair thing to say is that the right way to do this has not been worked out. But it's very promising. I mean, it does work quite well. I'll just give you a little bit of intuition based on this data set that everybody knows. This is the data set of handwritten digits. There are like 60,000 handwritten digits, 784 dimensions, like 28 by 28. Okay, so this is a case where you have 10 classes, okay, and there are 60,000 points. So you have 60,000, say, unlabeled points, and you have 10 classes. And you can use, so what the first step is to build a hierarchy, to do a hierarchical clustering of 60,000 points, okay? So let's see, what could we hope for that hierarchical clustering? Well, the best case is that we build this hierarchy, and right at the top of the hierarchy are these 10 clusters. There's a way to cut the tree so that you get exactly 10 clusters, and they're all completely pure, right? That's the dream scenario. The worst case scenario is that you keep going down the tree, and it's just everything's mixed at every level. And the only time you get pure is when you get to the leaves, to the 60,000 leaves. So the question is so clearly a scheme like this is going to do best when it's more like the first scenario than the second, okay? And so what does it look like? What does it look like? And here's the graph, and it shows that, when you get down to, say, 50 clusters, it's actually pretty pure. It's below 10% error. Okay, and so it's not the dream scenario. It's not just 10 clusters that are pure. But once you get down to about 50, everything is pretty close to pure, and after that it just tapers off pretty gently. Okay, and so this is a scenario that is in which one can expect to do well. Okay, and sure enough, one does. You can draw the curve, and it's way better than as one would expect. So this is a scenario where you get to 50 clusters. So you have big clusters that are relatively pure, and so a method like this is going to do well. Okay, and so so one last thing I wanted to point out is that I talked about a bunch of methods, but they're actually solving two different problems. The first two methods are solving what I would call active learning, where the final product is a classifier. Okay? The final method is not producing a classifier at the end. It's just labeling the data set, okay? And I think that that's much better than the first, okay? And that's a problem that we can formalize. I sometimes just call it the finite population annotation problem. So just get classifiers out of the picture altogether. So you have some data set. Each point has got a label, which is missing. You're allowed to query any label you like. You're given some epsilon and delta. And you want to label the entire data set so that at most epsilon fraction of those labels are wrong. Okay, so you're given a data set. You're not asked to produce a classifier. You're just asked to label the whole data set. And you're given a threshold. You're told, okay, you can ask for whatever, you can make whatever queries you like, query some labels, fill in some other ones, but at the end of the day, I want at most 2% of the labels to be wrong. Okay? And the reason I like this more than the traditional active learning scenario is that the usual way one uses this, okay, so you get a new data set, and you don't know anything about it, okay? So you have this new data set, you want to build a classifier, and so what is the first thing you're going to try? Maybe a linear classifier. So you said, okay, let me get a linear active learning algorithm. So you have this active learning algorithm that is fine-tuned for linear classifiers and is asking for points near the boundary. So you fit a linear classifier. But then you realize that the linear classifier is not so good. Maybe you needed a quadratic classifier. So now you pull out a quadratic classifier active learning algorithm, which asks for a completely different set of queries, okay? Because it's optimizing the quadratic boundary. And then that's not good enough. So then you decide, okay, well, maybe I need a neural net. So then you pull out a neural net active learning algorithm, which asks for a different bunch of queries. So somehow the traditional model of active learning is not, does not work well with this sort of multiple rounds of refinement in which we often end up dealing with data sets. And so this would work much better. Okay, where you just label the data set, and now you have this labeled corpus with a nice error guarantee. Okay, some of them are wrong, but at most 2%. And now you can apply whatever method you like. Okay, but this is something that, sort of just formally dealing with this problem and coming up with good algorithms for it is very much an open area. Okay. Okay. Well, thank you very much. Sorry? Yeah, active learning is very widely used, in all these vision, NLP, and it's just because, the labels aren't there, so it has to be used, yeah. It's used across the board. It's especially important in cases where labels are super expensive, like in some biology settings, where each label is a lab experiment, something like that.